Hello guys, this is going to be a workshop by Intellipaat on the topic of big data analysis with HDFS and clustering. We're also going to be discussing certain ways in which HDFS can be enhanced. But for those of you guys who are new to this entirety of big data and HDFS and MapReduce and everything, firstly we'll go through some basic introduction as to what the concepts or whatever we are discussing today are. First thing that we absolutely need to understand is certain distinctions, right? We need to understand what big data is in general. So let us go through the introduction to big data itself. So before we actually understand what big data is, do you guys understand what data is in the most fundamental format? So data is the individual unit of information that is defined as figures or facts and stored for later processing. So you have essentially data as the individual unit of information that is present on computer. This could be as short as something as 1 bit or as big as something as 1 petabyte. So you have data essentially present on your computers in three formats, and the first format is structured data. Now, structured data is what you see in relational database management systems such as Oracle DB or MongoDB, where the data is stored with exact column names available to you, and the data is stored in those column names. Basically, the data can be queried using SQL commands. In the case of MongoDB, it can simply be called for. So that is data which is essentially stored inside a database in a properly structured format. So that is structured data. The second one is semi-structured. Now, this is essentially in the form of files. What does that mean? Data can be present in an SQL table or a NoSQL table, but data can also be present in a semi-structured format where it's simply present in your file system. So what does that mean? Data can be present in a JSON file format or XML file format or CSV file format. Something like CSV means comma separated values. So that essentially means that each data point has a comma delimiting it from the next. So basically, it specifies to the computer, it tells the computer that data points are separated by commas. So that is what the CSV file format is. So since it has some structure associated to it, because the data is separated by commas, there's some syntax that is there in the data. It's not completely random. So that is why it's called semi-structured, because it does not have exact column names and everything. It's not arranged in the form of a table, but it still has some structure to it. So that is why it's called semi-structured. Finally, you have the most random form of data available, which is unstructured. So if you ever try to essentially, if you have an image file on your computer, if you simply open with a text file, if you open that image file with a text file, you'll see a lot of gibberish on your computer screen. So that is basically what unstructured data is. Now, unstructured data has a completely different way of dealing with it. And essentially, these are three different types of data that you have. So from this, what do we understand about big data? Any data set that satisfies the 5 V's of big data can be classified as big data, right? So if any doubts have come up, just look at that for a second. If any doubts ever come up, you can simply type those doubts in the questions box that are available on your right-hand side. All right. So, okay, now that we know what data is, essentially any data that satisfies all of these 5 V's or 5 criteria can be termed as big data, right? So if the data has velocity, so first point that we have is velocity. So that means the data should be coming in speed. The rate of the data should be really high. So say if you have a hard drive and the data that comes inside that hard drive from a streaming service, wherever you're getting your data from, comes in something like 1 terabyte per day or 1 petabyte per day. So that is good enough velocity for that data to be termed as big data, right? The second criteria that needs to be satisfied is volume. So volume means the size of the data, obviously. So if the data is in the higher gigabyte scale or terabyte scale or petabyte scale inside your file system, inside your hard drive, if it's like 1 terabyte onwards or in the higher ends of gigabytes, it can be termed as big data. Then you have variety. So variety means that the data cannot simply come from one source or the data cannot be in one file format itself. So whenever you're dealing with big data, the data types and the locations, the sources of the data can differ. So say if you have two data sets available, one is user data, one is sales data. Those two are being fetched from different databases and combined together as big data in your big data location. So that basically accounts for variety. Then you have veracity. So veracity means that the data should be inconsistent in nature. It should have some imperfections in it. Any form of big data collected from any source, be it Amazon, be it Google, be it Facebook, will have mistakes in it. When you're dealing with the scale of petabytes, the data will have mistakes in it. Some information will be entered wrongly by the users themselves. Some information might be missing due to data corruption. Some information might be not of the model that you're predicting it to be. So that basically accounts for imperfection and noise. So that is veracity. Data in any practical form cannot be perfect. So that accounts for veracity. And then finally, we have value. So whichever data that you're picking up for your big data analysis should have value, because if it does not have value, it cannot be termed as big data. So say in an academic database, right, you have your roll numbers for each of the students. Then you have names for each of the students. You have their sections. You have their grades, their percentages, their academic performance. So the data here that is useless is their roll numbers, because you're not essentially dealing with anything of information there. The roll number does not give any insight about that student. So you cannot make a model, or you cannot predict anything with that roll number. You cannot analyze anything with that roll number. So even if you have petabytes of roll numbers available to you coming in at high speeds with inconsistencies in it, you still cannot be accounted for big data. It still cannot be called big data because it does not have value. So that is what value means. So these are the 5 V's of big data. In order for data to be called big data, these 5 V's have to be satisfied. One doubt is regarding certification. The certificate will be sent to you on the email that you register to this webinar with. It will be sent to you after you've completely attended the session, and it will be available on your email. All right. So, what is the difference between semi-structured data and unstructured data? So unstructured does not have any order to it, and semi-structured does have some order to it. So semi-structured will have something like commas to separate the data points. Unstructured will be completely random in nature, and it is up to you to categorize it as you see fit. So let's look at what's next. Let's talk about Hadoop, MapReduce, and HDFS, because to tackle big data, we need technologies that are suitable to tackle big data. So what would be your normal approach to tackle big data? If you're thinking simply that you can simply add big data to your home computer in your hard drive and simply perform your analysis on it, so that is the most inefficient way to do it, because oftentimes you'll find out that you don't have enough hard drive space. And even if you have enough hard drive space, your one CPU, doesn't matter if it's i9 or i7, even if your one CPU cannot handle such large scales of data on its own, right? So individual computers certainly cannot certainly cannot handle big data processing and storage, essentially. So then comes in, what if we combine a lot of computers together? So that is what the concept of big data clustering is. You combining a lot of computers or hardwares together, or server farms together, to basically achieve data parallelism, where you are simply combining the efforts, simply combining the processing power that is available on all of these hardware, and using that to process your cluster to all of these systems, and all of this. That is how big data clustering. So let's talk about two elements that are basically implement this today world, right? So Hadoop is a technology that helps us implement this, and it has two elements: MapReduce and HDFS, which are the services that are present in the Hadoop framework that help us achieve big data clustering. So let me look at if any doubts have accumulated. If you guys are facing audio issues, it might be due to your internet connection, because a lot of people are not facing any audio issues. So you can try reconnecting to the webinar, and it might get fixed. All right. Can we learn both big data and data science? So good question. The thing about that is obviously you can. So the way I would recommend you to do that is simply uh, understanding if you're coming from a data science background or a data analytics background, it's very easy first of all to get into big data. But if you're not, if you're simply going for big data as your first career choice, then it becomes even simpler because you'll by the end of your big data learning experience, you'll know how to handle data very precisely. So what that will do for you is that when you're dealing with data science, you're going to be dealing with Python and R in general. And if you know how to implement big data with data science, you'll be able to create even more precise insight models because you're not simply dealing with megabytes of data. You're going to be dealing with you have the ability to deal with even terabytes of data, 2 petabytes of data in your simple data science module. So that is the advantage of it. You learn everything that you need to learn for your data science Python course, but knowing this, having this knowledge about big data, you can implement that in your Python code as well. So that is all. You don't need to basically change your code or code as much or anything. You can simply import some libraries and you can achieve that. So let me go through how big data actually works. So firstly, HDFS. HDFS is Apache Hadoop's service that is present on top of the Hadoop framework. HDFS is short for Hadoop's distributed file system. So similar to what you have on your computer right now is a if you have a Linux file system, it's called simple file system that is using your hard drive that where your operating system is basically using your hard drive to store data, right? In HDFS, a section of your hard drive depending on the data that is being put inside your HDFS, a section of your hard drive is reserved for your data. What will happen is a certain portion of your, but that is also not simple overdriving of the storage. What happens in HDFS is that you can reserve some amount of hard drive space in a lot of computers, install Hadoop on it, right? And you can connect them all together in a network. So what happens when you do that is that when you connect them all in a network, you can use all of these storage spaces to basically divide any big data that you receive in the server throughout all of these nodes. And what happens then is then you can process that data in parallel using the computational resources present in all of those systems. So let me go through the definition. HDFS is a file system designed for storing very large files with streaming data access patterns running on clusters of commodity hardware. So when you're dealing with very large files, you can use HDFS for that. Commodity hardware here means that you don't have to buy any expensive servers. You don't have to buy any expensive hardware. You can use your normal day-to-day usage devices and simply connect them to your HDFS network, and they will act as optimal storage devices for your HDFS server. So the way that happens is that you're going to be using a lot of devices in conjunction. So you don't need to have high specifications on any particular device to achieve this. So very large files in this context means the files that are of hundreds of gigabytes, terabytes, or petabytes in size. And then streaming data access. Each analysis of the data set involves a large portion of the data set. So the time to read the whole data set is more important than the latency in reading the first record. So what that basically means is that when you're dealing with a large portion of data, then the best way to go about it is actually understanding the time that it will take to analyze the entire data, keeping that in consideration rather than the latency of the job that you have. So when you keep the entirety of the job in consideration, the time that is being taken to complete the entirety of the job, you can essentially ignore all of the other elements like how fast your RAM is and whatnot, and then simply execute it depending on that time. Then you have commodity hardware, so it's cheap. You don't have to pay a lot for that, and it's simple devices as well. Right. Let me look at some of the questions that have accumulated. All right. So some people are saying that there are some audio issues, but some people are saying that the audio issues are not existent. Maybe it's a server problem. All right. Let me look at some other questions. I think the audio issues have resolved. Have they been resolved, or is it still breaking for the people who are saying it's breaking? All right. So, okay, it's not breaking anymore. All right. So, okay, a lot of questions. I'm not going to be able to answer all of these questions. So, let me start with first. So, what does commodity hardware mean? Commodity hardware essentially means that, okay, let me explain that concept to you. So, what happens traditionally in these cases is that companies, when they are trying to analyze data, they often have to install these huge server rooms in their office premises, right? These server farms or whatnot. And they have to dedicate an entire room for those servers. So you have to invest a lot in that, and you have to hire a administrator team, or you have to hire a maintenance team. So you have to do all of that. But with commodity hardware, what happens is that every computer present in the office building that your day-to-day employees use, Hadoop can be installed on those computers, and in the LAN connection that you have, in the local area network that you have inside your office premises, that can act as a connecting glue for all of those systems, and then you can simply use the entire office device, all of the devices that are present inside your offices, all of the computers, as your HDFS server instead of dedicating an entire server to it, right? So that is why commodity hardware is such a point in HDFS, because it reduces your expenses. All right. So any other doubts in here? All right. So let me continue now. So what is MapReduce? MapReduce is the processing model that is present in your after your in your Hadoop, basically. So HDFS will store the data. The distributed file system is what is used to store your data. MapReduce is used to basically process that data. So depending on the program that you've written, depending on the Java job or your PySpark job, not your PySpark job in particular. PySpark will use a different programming model. Depending on the big data job that you've put in inside your HDFS, you can use MapReduce. Hadoop provides a processing framework for that. We'll go through how this works when we reach that slide, firstly. So let us go through the definition first. MapReduce is a programming model suitable for processing huge data. Hadoop is capable of running MapReduce programs written in various languages. So MapReduce libraries are available for Java, Ruby, Python, so on and so forth. MapReduce programs run in parallel in all of the commodity hardware. So the job will be divided in parts, and it'll be executed. It'll be executed in parallel in on all of those devices, depending on the data block that they've received. So they execute in parallel and reduce the time that it would have taken for the job to complete on one system by a drastic amount. So before we get to the architecture, if any more questions have accumulated, uh, Ganesh is asking, can big data be integrated with SAP application? Not necessarily. SAP applications don't have a direct big data library integration with them, but there are ways in which you can achieve that. So, whatever logic that you're trying to implement with your SAP applications could be implemented in coding format in say Python or Java. So you can use MapReduce to achieve that. But the best way to go about it would be using Apache Spark. So yeah, SAP applications definitely big data is achieved with them, but not necessarily with Hadoop or the traditional big data tools. There are other services for that. So the architecture for HDFS. The HDFS architecture seems something like this. All right. So let me just explain to you how data is uploaded in the HDFS. So firstly, you will create your cluster, you'll create your big data cluster by connecting all of the commodity hardware together. So here we can see that there's a name node, there are three data nodes, right? So all of these blue boxes, right? These are computers. These are commodity hardware. Assume that, right? So one computer can be made the name node, and three computers with, say, these three computers have high storage, say something like 1 TB storage hard drive space each, right? And this computer only has, say, 200 GB storage. So it has the 200 GB storage computer would be made the name node, and the three computers with 1 TB storage will be made the data node, and they're all connected together in a local area network, preferably, right? So then you have a person who wants to upload some big data, right? So that is your HDFS client, because he's a client who's going to be interacting with this entire HDFS server. These combination of these four blue blocks. This is the HDFS server, and the client is going to be interacting with that, right? So when the client uploads that 1 TB or 1 PB file onto the HDFS server, the name node basically looks at the file and says, okay, this file is this big, and I'll have to divide it into multiple parts in order to fit it across these three data nodes. So I said petabyte, but let's not talk about petabyte here. Let's talk about only 1 TB here, because these data nodes only have 1 TB space, right? So what the name node will do is simply cause a division in the file. So it's a 1 TB file. It will be divided into three parts, and these three parts will be stored on data node 1, data node 2, and data node 3 respectively. So these three data nodes have three parts available to them. So data node 1 will contain the first block, data node 2 will contain the second block, data node 3 will contain the third block, right? So what the HDFS will do now is it also implements a data integrity and safety mechanism. So in order to preserve the integrity of data, say if data node 1 fails, right? But you want the data to be backed up. You don't want the data to be lost, because without the data present in data node 1, the data present in data node 2 and 3 will be useless. So whenever the block is sent to these data nodes, they also replicate amongst each other. So whatever block was sent to data node 1 is replicated and sent to data node 2 as well. If the replication factor is 1, if the replication factor is 2, it will be sent to data node 2 and data node 3, and the block will basically have three combinations, right? So even if data node 1 fails, the first data block will be there in data node 2. So that is how data safety is maintained. So anyway, so that is how data is uploaded onto the HDFS. And whenever a client has to read this data, he'll simply access the name node. The name node will basically point to where the data begins. So the first pointer will be at data node 1. So this contains the first point, the first data block, and the second pointer would be at data node 2, and the third pointer would be at data node 3. And whenever the client tries to read that data, it will basically, the name node will give the client a combined view all of these three data nodes. So that is how big data is stored on your HDFS architecture, instead of storing it on one system itself. So let's continue and look at the processing framework, which is MapReduce. So firstly, let us discuss one other way in which we can store data in HDFS, which is what we call as the data aware HDFS model. So this is a proposed theory. So what happens in this is that you have your data that is of various file formats. You can have MP3, JSON, XML, CSV, JPEG, anything, basically, any file format that you can think of. So that is the whole jumbled up bunch of data that you have. And this is in big data format. So what you could do is simply upload all of this data together, and the HDFS will simply divide it as it would into other nodes, into the data nodes, and then replicate it. But the HDFS will not see the kind of data. So to optimize certain things, for instance, when large amounts of data are uploaded onto the HDFS might deal with scaling and performance issues alongside unnecessary power costs. So this happens when something as big as an MP3, because in MP3 and JPEG files, which are music and image files, you have to preserve the quality of data, right? So in order to do that, there can be no compression involved with it. There can be no sort of data fault involved in it. So in that case, a lot of hardware resources would be required to preserve the integrity of those data formats. But in the case of JSON, XML, and CSV, you can easily compress that data and keep it somewhere else as well. So in the HDFS itself, in a compressed format. So let us talk about what happens because of that. When you specify a certain hardware, say a certain hardware in your commodity hardware itself, there's a certain hardware which has high specifications like high RAM, high processing power, and high storage, good storage. And so what you could do is simply categorize your data into high quality or low quality and store the high quality data on the high specification hardware and store the low quality data like JSON, XML, and CSV on the low specification hardware. So that is what essentially the data aware HDFS is. Programming in a script in the HDFS configuration, which basically separates the data by file format. So whenever you upload MP3, a specific number of nodes have been assigned for files like MP3. And whenever you're dealing with JSON XML, a specific category of nodes have been assigned for those low quality files. So in this case, you can simply use as only as much resources are required for your big data cluster, and you can keep the power costs to a minimum, and you wouldn't have performance or scaling issues because you're going to be dividing data accordingly depending on the hardware configuration. Processing data like MP3 and JPEG also takes a lot of time as compared to JSON or XML. So it is also preferred that your nodes, which are dealing with MP3 and JPEG sort of data, have a good CPU as well. So this is how you can essentially optimize your HDFS as well. So let's talk about the MapReduce workflow. Now that we know the storage, how storage happens in Hadoop, we will talk about how processing happens in Hadoop. So let's talk about MapReduce. So now we know that the D1 and D2 up until Dn are different data nodes that are available in your Hadoop cluster. So what happens when you run a job? When you run a big data job, all of the data blocks that are present for that particular job in these data nodes are sent to functions called mappers. These mappers will catalog this data. These mappers will assign key elements to these data, right? They will convert this data into a primary key and a value associated to that primary key in that format. So you'll have in one column, you'll have all of the instantly. So you can say enter primary and as the value respond to that primary instantly, make your job much faster. That is the mapper does. It maps that data with values. So it maps keys with values. It creates key value pairs. So that is the first job that happens. So that is the mapping job. Okay, you're dealing with a file which so the name is MapReduce, contains a lot of text, and you're counting the frequency of each of the words in that text, right? Available. Just a moment. Yeah. So you're counting the frequency of each of the words available in that text file, right? So in that case, you'll simply map the amount of times those words are appearing uh, corresponding to the word. So the word will be the key, and the number of times it appears in that block of text file would be the value. So when you put it into the reduction process, you will send the same words. You will send the data records with the same words to one reducer. So say this mapper has a word I, and this mapper has also the word I. They will both send the word I and the corresponding frequency of that word to the reduce function, this one reduce function. But say if the word am exists over here in this mapper and the word am exists in this word mapper over here as well, they will send the am to this reducer. So what this would achieve is that you can run this reducer in parallel with this, and you at the end of it, you will get the final count for I over here and am over here. So you do that task accordingly for a larger data set as well, and you achieve data parallelism. So these reducers can work independently. And at the end of it, when you combine all of these outputs from O1 to OM, you will get your final output, which would be the word count. So that divided your workload by three, the time that it would have taken for this job to be done by one system by three when you're using three different nodes. So basically that is what is happening in this particular case. So that is what the MapReduce operation does, and that is how Hadoop MapReduce works in general. All right, so let us continue. Okay, so one doubt. All right, so how is data parallelism achieved? Say there is, okay, so one question is being asked with regards to if these reducers are working in parallel. So say if there are certain boundaries over here, say that I is over here and over here as well, right? So if these are working in parallel, how would we get the final count of I if this particular reducer evaluates the I value to say 2, and this reducer evaluates the I value to 1? Wouldn't there be a conflict as to the final output of how many times I appears in the data file? So as I said before, that is not what happens in the reducers. Whenever you have something like I available, it will only be these mappers will communicate with each other firstly, and the eyes will exclusively be sent to only one reducer. So that wherever the key is same for all of these three mappers, even if this mapper has an eye, it will be still sent to the reduction part. So this particular reducer, and if there is another word that has been allocated to reducer number 2, it will be sent to reducer number 2. So that is why at the end of it, you get the final counts in a parallel format. Okay, so one question is being asked, does map and reduce run on the same nodes or separate set of nodes? They run on the same node. So the way that happens is, say, not entirely the same node, it could depend entirely. So say, for instance, you have your HDFS system that is combined together. You have your HDFS cluster that is combined. Uh, Say for the word I, the keyword I, it's being sent to reducer number 3, right? So if that happens to be on the same system as this mapper, if that reducer where it has been decided that this reducer will take the I words available, if that happens to be on the same system as as to where this particular mapper is running, then yes. Otherwise, this mapper will send the I output to reducer number 2 if the reducer number 2 is handling that I word. So that is how that happens. So let's talk about Hive. For the demo that we are going to be demonstrating for data analysis, we are going to be using Hive. Now, what is Hive? Hive provides an SQL-like interface and an abstracted query language, HiveQL, to query the data stored in databases and file systems that are integrated with Hadoop. So, such a file system is HDFS, which we just discussed today. Hive supports the analysis of large data sets stored in the HDFS, and it also has compatibility for file systems like Amazon S3 or Alexio. So if you have other file systems as well which deal with cluster-based computing, you can use that. So for instance, if you have your files stored in Amazon S3, you can use Hive with that as well. But right now we're going to be using HDFS. So what does HDFS do? You have your JSON, CSV, or TXT files, or any other sort of file format available in the HDFS. You've stored it in the HDFS. And then you have your data warehousing tool, which is Hive. So Hive will pick that data up from HDFS, it will warehouse it. And then whenever you run a query, whenever you write an SQL statement on Hive, what will happen is a MapReduce operation will run to actually execute that statement. So instead of doing it in the traditional MySQL format, you will be using MapReduce, Hadoop's MapReduce for that. And then after you've received your final table or your output, then you can generate your insights, you can get your reports, you can get whatever querying you're doing basically. So that is how Hive works. So in this particular tutorial that we're going to be doing in this workshop, I'm going to be using a virtual machine with a Linux-based operating system installed on top of it, which is CentOS, and we're going to be using frameworks, the Hadoop framework, and then on top of the Hadoop framework, we're going to be using Hive, which is the data warehousing tool. Yeah, so let us continue. All right. All right, so I've opened up a virtual machine already. So this is the Linux virtual machine that we are going to be using today. Log into the virtual machine. All right. So in here, if I simply go to my trainings home, in the normal Linux file system, not the HDFS, mind you, this is the normal Linux file system, similar to what you have on your Windows or your Mac PCs right now. This is the normal Linux file system. And in here, we can say that we have some files available. So the one that I'm going to be using today is the sudo underscore facebook.csv. So this is a Facebook data set, and it has certain records like and the number, the basically the primary key to that user, some things like age and whatnot. We'll go through all of that just a moment. So I have the column names available. Just a moment. Yeah. So as you guys can see, these are the column names that are there. So we are going to be creating our HDFS, creating our Hive table accordingly. So we have our user ID, we have our age, we have our day of birth, we have our year of birth, we have our month, gender, the amount of months that the person has been on Facebook. So I think these are the amount of days actually, not the months. The friends count, so the number of friends that particular person has, and the friendships that he has initiated. That means how many friend requests have they sent and have been accepted. The number of likes that that person has provided, and the number of likes that that person has received on his profile, the number of likes through mobile phones and whatnot. So these are the data records essentially. We're going to be analyzing this CSV data essentially, and through our virtual machine. So that is there available to us over here on our sudo facebook.csv, right? So let us analyze this. So first thing first, we'll actually have to upload this data on our HDFS server. So the way we do that is quite simple actually. Open up our terminal. Once we've opened up our terminal, I'll just expand the text so you guys can see. Firstly, let us type the location, just create a folder in the HDFS in our HDFS server to actually do this. So Hadoop FS, whenever I type Hadoop FS, I'm actually dealing with the Hadoop file system, which is the HDFS instead of my normal Linux file system. And I put in the dash and I type in mkdir, which is make a directory, which is make a folder. And let us call this folder Hive webinar. So we've created a folder called Hive webinar inside our HDFS. So the next thing that we would do is actually transfer our file from our Linux file system to our HDFS. So Hadoop FS and PUT. Whenever you use put command, you can, the first parameter for this is the file present or the file location in the file system that you have, which is in my case, let me look at the file name once. Sudo underscore facebook.csv. So sudo underscore facebook.csv. So this is the file on my Linux system, and then I'll simply given the folder name, which is Hive webinar. So it will be uploaded to that folder. So to verify this, whether it has been uploaded or not, I'll simply type in Hadoop FS and then hyphen ls. ls lists all of the files present in a particular directory, and then I will type in Hive webinar. So as we can see clearly that Hive webinar slash sudo underscore facebook.csv, it has been uploaded onto our HDFS. So if you're having a big cluster, a big office cluster in your own workspace when you're dealing with big data, the exact same procedure will be followed for that as well. It will basically upload it, and if the file is extremely large, for instance, if it's in the gigabytes or terabytes, it will be divided into different blocks. But in here, whenever you type in ls Hive webinar, you'll see it as one file itself, right? So that is the advantage that you get with HDFS essentially. All right, so let me continue now. So now we have put the file in the source location, and now what we will be doing is actually warehousing this file. So we'll create another terminal, expand this, zoom in a bit so you guys can see. Okay, so to start Hive, I'll simply type in Hive. Now we're inside our Hive terminal. So it works in a similar fashion to SQL, if you guys are familiar with MySQL. So if you type in show databases, it will show you all of the databases that are present in your in your Hive warehouse. So in my case, let me use something like YT session. So use YT session. Now we are inside the YT session database, and now we can create our tables. So in order to create the table, what we will do is simply type in create table. So the way I would go about this is actually opening just a moment, actually creating a document over here so that I'm able to write my entire query first before I actually execute it. So let me create sample query, open that up and type in my command, which is create table. And let us call this table webinar Hive. So now is the time where we actually correlate to this data, correspond to it, and create our table accordingly. So the first is user ID, which is an integer value. So you'll type in user ID and int. Next is age, which is also an integer value. So type in age and int. Next is day. So day is also an integer value. It can only be 1 or 31, 1 to 31 essentially. So let's call it day and call it int. The names don't have to match. So you can call it day and you can say dob underscore day in the data set. It does not matter. Then you have year int, because year cannot be more than an integer value. Then you have month can also not be more than integer. Then you have gender. Now gender has to be a string. It can be male or female. And then tenure has to be integer. Then you have friend count. So let's call this friends. So that is an integer. And then afterwards, let us look at what we have. Then we have our friendships initiated. So friends init, let's call it that and call it int. Then we have likes received. Likes, first let's call it likes int. And then likes, let's go back over there. Likes received, let's call that int as well. Mobile likes, int mobile likes received, which be an int as well. And then we have web browser likes. Web browser likes are www likes, int, and www underscore likes underscore recd, which are likes received, which we an int to. So I think that is the last data column that we have. I think pretty sure about it. Yeah, so no more data columns after that. So this could be dealt with and we can go back to this. So the next thing we would do is specify the delimiter. Since it is a CSV file, we're going to be specifying the delimiter as comma. So we'll firstly say the row format delimited, and the fields are terminated by, and then in the string double quote, we will write single quote, we will write comma. Moment. And after we've written that, we will simply give in the stored as a text file and specify the location for it. Now the location has to be the absolute directory present in your HDFS. So within the single quote, I'll simply type in /user /training and Hive webinar, and then simply give in the record name, which is sudo underscore facebook dot csv. We close that up, or we can simply remove this as well, and it will take up all of the data present inside that particular folder. So that is how big data works in general. So all of the blocks that would be present inside the Hive webinar folder will be taken up. So let us continue after that. Put in a semicolon over there. I'll copy this entire thing up. Go back to my Hive terminal. Just a moment. That is not the Hive terminal. This is the Hive terminal. Paste it over here, and I'll press enter. So the query is okay. It was executed, and we can see the table now. So we'll type in something like select asterisk from webinar Hive, and limit the number of records that it would display to something like 3, so that it doesn't fill up the entire screen. And we can see that we have our data records available to us, right? We have our data in the form of a table. So we can essentially analyze this data now, because earlier it was in the form of a comma separated value. So we can see the distinction right now. So this is also the task of a data analyst. The earlier data that was available to us was in this particular format, where it is divided by commas, no particular format associated to it, semi-structured in nature. But what we've managed to do now is converted it into a table. Now it is in a structured format. This is an SQL-like table, and we can execute it, we can query on it like SQL simply by using Hive. So you can see that if you are not able to use something like an MySQL database to analyze big data, MySQL can analyze small amounts of data really easily. But when you're dealing with big data, this is the way to go. You can use Hive to perform queries on that data. Anupama is asking, what is the difference between the HDFS and Hadoop command? There is absolutely no difference between the HDFS and Hadoop command. It's just a matter of version difference. Earlier versions used to use Hadoop FS. The current versions, they prefer to use HDFS FS. But the commands exactly do the same thing. And I don't think any of them have been deprecated. So you can use them alternatively. Is there an IDE that can be used for Hive? Yes, definitely there are IDEs available. So if you're using something like Hue is a UI-oriented implementation to implement your big data tools on. So if you have a Hadoop server already installed, you can install Hue on top of it. And whenever you access your Hadoop server with Hue, you can use Hive from a UI-oriented standpoint rather than using the command line terminal. So that is another way you can go about it. So I hope that makes it clear. How do we decide the amount of data or file that can be processed by our server? So there are multiple ways you can go about that. It just depends on you knowing how much data you can actually store. So it will basically give an error message if the data cannot be stored by your big data cluster, if it's that big. If it does not lie within the HDFS constraints that have been put into the configuration while you're installing Hadoop. If we have a 50 plus column name CSV file, so we can write all of the column names whenever we create the table in Hive. Yes, you can. And if the question is from a standpoint as to if it will be too tedious or something, then Hive has that limitation. You cannot simply, uh, not write all of the column names. If you're warehousing data, you have to specify which exact columns would you want. So if you say something like if you don't want particular columns in your data, then you can refrain from writing those. But if you want all of the column names that are available, you have to write all of them. How do we create primary key if needed? So the primary keys would be created in the same format as you would do in your normal SQL. But since whenever you run a query, while you're using Hive, whenever you're actually running a query, the MapReduce job will automatically happen. So you don't necessarily need a primary key. If your MapReduce job is already on its own going to create some primary keys. So yeah, data does not need to be cataloged when you're dealing with Hive. The MapReduce will automatically catalog it upon requirement. Any mapping that can be derived on the size of data and server configuration. So obviously, I mean, you cannot fit in it. Depends, right? I mean, the processing limits are not there. So if you have a job that requires a lot of processing, the processing will happen endlessly if your computer is not, if your hardware is not capable of handling it. It'll happen for a longer period of time. But as far as storage goes, definitely if your storage requirements do not match with how much file, the size of the file that you have, it will definitely not be stored on your server. So that is pretty obvious. Any other doubts? Yeah, Saurabh is asking, can I load a specific column CSV data in Hive table? Yes, you can do that. So in that case, you will be using some additional scripts like surds. Instead of putting in a delimiter, like I put in a comma, you'll be using a surd, and that surd will basically match all of the column names that I've just entered over here, like user ID, age, and day. Instead of actually not having them actually matching. Like in this case, I matched column names like user ID, but something like day. Day over here is, if I scroll back over here, day over here is DOB underscore day. I've just written day. So in my particular aspect, I have to match all of the. I have to match the column pattern. I don't exactly have to match the names. But when you will be using surds, what you'll have to do is you will have to match the names, and only the names that you've written, right? Like if I've written user ID and nothing else, after that I've closed the bracket. The only column that would be picked up, it will be user ID. So in that case, you have to make sure you match the names and use a sort. So if that is the doubt, that is the answer to that particular question. Hadoop supports all sorts of data. One question was, what sort of format of data does Hadoop support? You can store anything inside the HDFS, but it depends, right? If you're analyzing it with Hive, it needs to be semi-structured. If you're analyzing it with Hive, it either needs to be JSON or CSV or something. It cannot simply, come from a random MP3 file. You cannot warehouse data that has no structure to it. So yeah. All right. So let us continue now. Let us just perform some simple SQL queries, and we'll just see how MapReduce is actually functioning. So if I type in something like select sum, and I want to find out the average age of the Facebook user, how would you go about it? Let's type in AVG instead of sum, right? So this is where we can play around with things. This is where the data analytics come in. So if your employer asks you, what is the average use of the Facebook user? So you'll simply type in average and age, and then you'll simply type in from, and then you'll give in the table name, so webinar Hive, and then you'll put in a semicolon, and a MapReduce job will start. So this MapReduce job is starting because it's assuming that the data that we are dealing with is a big data set. It's not actually accounting for the fact that the data that I've actually used is under 2 megabytes. But the advantage of that is, even if my data was a terabyte in nature or a petabyte in nature, and if I had a good enough big data cluster, it will still do the same job in the same time. So you might be wondering that if I did this with a normal MySQL, we would have achieved the output in a faster time. But what happens when you're dealing with big data, right? Your SQL cannot match with the performance of a MapReduce job. So even though it took a longer time to calculate the 37 age demographic, but if we are dealing with petabytes of data, it would still have taken around the same time, although the SQL would not have taken the same time. It would have taken considerably longer to do the same. So I hope that is clearer. Let me just go to the bottom over here, and let us perform something else. So what do we want to do now? So let us just find whether females or males get the most amount of likes. So in this case, we will simply use a group by, right? So what we would do is group the sums of the number of, say, likes that people are getting according to the gender. So we will type in select, we'll type in something like gender. So gender is the column name that we're using for gender. And then the next thing that we would be using is likes received. So let us use this one, which is the likes underscore RECD. So sum, let us use average likes underscore RECD and from, and then we put in something like the table name webinar. What was the table name? Hive webinar, I think. Webinar Hive, and we get type in group by gender and put in a semicolon and start the MapReduce job. So we can see that there are specific genders. So the people who have chosen not to specify their gender on Facebook have a average likes of 157. Females have a average likes of 251, and males have average likes of 67. So we can see some certain gender-oriented gender-oriented analysis that females tend to get more likes than males when using social media platforms. That is something that we already knew, but with this data, we were able to prove it. So that is how data analysis works with big data in general. So say if you had a terabytes of data available to you from Facebook, then you would get an even more accurate representation of how this happens. So let us continue with something else. Let us find something more interesting that we can do with this data. So let us find the average age. So I think that would be, and I think we've found out the average age. So let us find something like, let us find the number of friends, basically. Let us find with certain age demographics, the average number of friends for each age demographic. So let us find the average number of friends for, say, age demographic of 13 to 25, because 13 is the minimum age for Facebook. So let us find that. So select average age, where age greater than equals to 13 and age less than equals to 25, and semicolon, enter. So what wrong? Okay, we didn't actually add table name, just a moment. From That is the table name, or webinar Hive is the table name. So let us see the average age. We actually calculated the average age. We had to calculate something else. I apologize for that because, okay, so average age is 12, but average age is 19, but let us find something else. We have to find out the average likes received, average friends actually. So average friends that people have added in their accounts from the age demographic of 13 to 25 would be 268. So at an average, people with the age demographic of 13 to 25 have 268 friends on Facebook. But if we just change that number and make it 25 and above, so what happens then? So let me see if any doubts, not particularly any doubts. So one person is asking, depending on the amount of nodes that I have on my cluster, will the job be performed faster than this? So will it always take the same time or not? So yes, obviously, depending on the cluster that you have, depending on the amount of nodes that you have, and depending on the data size that you have, right? Uh, it all depends whether your cluster has faster processors in their nodes, whether the cluster has the appropriate amount of RAM that is required to perform these jobs. And depending on that, yes, you can achieve this work much faster as well. Is Hive query similar to SQL query? Yes, it's almost identical. There are certain things that you can do in SQL that you cannot do in Hive, but with SQL, you can certainly not handle big data. So Hive definitely trumps SQL in that regard. But yeah, it's the syntax is almost identical. The with the functions and how you would write these things, it's almost same. Yes, the map and reduce speed entirely depend upon the system configuration of your big data cluster. There's no other category to basically describe. System configurations, not just the single system configuration. It depends on the system average system configuration throughout your cluster. So yeah, I mean, yes, we are using commodity hardware, but we cannot be using absolutely cheap hardware. We need some sort of integrity in those in the hardware that we're using. We cannot simply use something with an Intel Celeron CPU and say 200 or like 100 gigabytes of disk space and 256 MBs of RAM. So that would be quite less for big data processing. So you need something like an average level. You don't need something on the advanced end in you as your nodes, but you certainly need computer systems which are average in performance and storage. So system configuration for worker node or master node. So yeah, master node can afford to be of a cheaper configuration because in the master node, data is not being stored or processed. Although you can configure it too, but just generally does not happen on the master node. Master node only stores the metadata. It only coordinates the jobs. It allocates the resources, but it does not actually partake in the job performance. So master node can be cheaper. The slave nodes have to have average configuration. All right, so we can see that job has been formed and people above the age of 25 get an average number of friends of 141, while people with in the age demographic of 13 to 25 get 268 friends on an average. So you can see how these solve real world use cases as to now now Facebook would know how their audience is reacting, how many people are active on Facebook and whatnot. So there's also another data column that we can use. We have mobile likes saved, right? And we have mobile likes in general. So what we can analyze from this is www likes is basically the amount of times the person has liked from his Facebook account using his web browser, while this is from the mobile application, right? So we can find out the usage of mobile phones and web browsers. We can find out the comparisons between that. So let us find that out. So let us select. So we're finding out the average mobile likes and average in the web browser likes for the age demographic of, just a moment. So we'll find out the age between the age demographic of 13 to 25, what is the average number of likes performed with a mobile phone versus a web browser. So we can see with a mobile phone, about 123 likes have been performed, and with a web browser, 55 likes at an average have been performed. This gives us an idea of the usage, right? So we understand what is the usage like. On an average, people of this age demographic use the mobile phone more than they would use the web browser. So let us find out this for a demographic that is above this. So age greater than equals to 25. MapReduce job run on the worker node. Yes, MapReduce run generally run on the worker node. Although you can configure it to somewhat run on the master node as well, but that is generally not recommended. Yeah. So we can now see that even in the older age demographics, people are more accustomed to mobile phones, although they use it quite less than compared to the younger generations. And yeah, they use web browsers quite less than mobile phones. This is consistent throughout all age demographics, I would say. Some just one more query, I think, and then it would be it. So let's find on an average, do females initiate friend requests more, or do males do that? So we can do that as well. So a lot of things can be revealed. So select at an average friends. I think what's the column name? Just a moment. Friends in it. Okay. So friends underscore in it, and the other column name would be gender. And then we will find out from first webinar 5 group by gender and start that query. So we will find out on an average which gender initiates the higher number of friend requests compared to the other gender. So we can see that that is something quite surprising, although. All right, so 92 people who haven't disclosed their gender and have an account on Facebook, about on an average, they generate 92 friend requests. Females generate 113 and males generate 103. So that's quite close, not a discernible difference, but yeah, we get those differences. All right, guys, so we'll be ending the session right now. Thank you so much for attending. Hope to see you again next time. Thank you.